So for the past few weeks, we've been learning about atomic structure and how atoms are actually built. We know that protons and neutrons are going to be found in the nucleus, which is the center part of the atom. And we also know that there are electrons in what is called the electron cloud, which is on the outside of the nucleus. And those electrons live in energy levels, also known as energy shells. And so today we are actually going to talk about stability in chemical bonding. So we get to the fun part of chemistry where chemical reactions are going to start taking place. But we have to learn why they take place before we can learn how and all the fun stuff. So I'm going to have you guys go on ahead and create an outline for Chapter 20, Section 1, and I want it labeled about like this. You can pause the video if you want, if you're watching this at home, to write these things down. But we are learning about Chapter 20, Section 1, Stability and Bonding. You can find this information on pages 602 through 606 in your book. And your outline should look something like this. We'll talk about combined elements, compounds, and how those compounds have new properties that are different than the actual elements, different formulas. We'll review element symbols, and we'll also take a look at what chemical formulas tell us. And then we'll also look at atomic stability, why noble gases are actually stable and they don't react with other things. We'll talk about chemical stability and different energy levels, filling those outer energy levels. And then we'll also talk about why stability is reached when chemical bonds are formed. So again, if you need to pause this to finish writing this down, you can. Otherwise, I'm going to go on ahead and move on. So we're going to talk about how compounds form and combined elements. And a compound is simply nothing more than two or more elements that have formed together to actually make those elements stable. And very few elements in nature are actually going to be found by themselves. Most of them are going to be found in what we call chemical compounds. And those chemical compounds have new properties. For instance, we talked about sodium being very, very reactive because it only has one valence electron in its outer shell. So sodium cannot be around water or it'll actually kind of sort of explode. But when sodium reacts with chlorine gas, for instance, it'll give an electron away, and that electron goes to chlorine. Chlorine is also no longer reactive, and it forms a very edible compound. In fact, you eat that compound in almost every single thing you eat, and we call it table salt or sodium chloride. So the next thing we're going to talk about, we're going to review chemical symbols real quick, and then we are actually going to talk about compounds and what they look like. Okay? So this is the periodic table. I know you guys have seen this because you've used them on tests and we've taken a look at them almost every single day. And there's a little box up here that actually tells you how to read the periodic table. I know it's kind of hard to focus in this video, but you kind of get the gist here. But you've got your element symbol in there, you've got your atomic number, your average atomic mass, also known as your atomic weight, and then also the element name. And those symbols are basically like shorthand for the name of the element. And those chemical symbols are going to be used when we write chemical formulas. And so to talk about chemical formulas, they're great and they tell us a whole lot about a compound. Those chemical formulas not only have the information of what atoms are in the compound, they tell us how many of that atom is in the compound. For instance, right here you have the chemical formulas calcium oxide and magnesium hydroxide. And calcium oxide looks like this, CaO. And you can see that calcium oxide has one atom of calcium and one atom of oxygen. But in magnesium hydroxide, you see a small number at the very end of the OH, and you also see some parentheses. Magnesium, there's only one atom of it in this compound, but you can see that OH has parentheses around it, and then there's a 2 on the outside of that. That 2 is called a subscript. And that subscript tells me how many atoms are in those parentheses. Sometimes there aren't parentheses, but in this case there are. And so that 2 is applied to everything within the parentheses. And basically what it means is there are 2 atoms of oxygen and 2 atoms of hydrogen in that compound. So altogether in magnesium hydroxide, there's 1 atom of magnesium, 2 atoms of oxygen, and 2 atoms of hydrogen for a total of 5 atoms in that one single compound. And those chemical formulas, again, are incredibly, incredibly important because they tell us exactly what's in a compound, and that's a very, very fixed ratio. If you change anything, any number of elements in that compound, it's not going to be the same compound anymore. Okay, so now we're going to talk about atomic stability. And we've talked about noble gases a little bit already, but we're going to kind of review them. We know that those noble gases have a full outer shell, and that full outer shell has 8 valence electrons in it. And because noble gases have a full outer shell, they are not reactive at all. They don't want to gain any electrons, and they don't want to lose any electrons. In fact, all elements in group 18 have 8 valence electrons in that outer shell, and they are not reactive at all whatsoever. Here I have an example of neon. Neon is element number 10. It has 10 protons and 10 neutrons in its nucleus. It has 2 valence electrons, I'm sorry, not valence electrons, but it has 2 electrons in its inner shell. And then in its outer shell, it has 8 valence electrons. And because that outer shell has 8 valence electrons, neon, a noble gas, is not reactive at all. We're going to review those energy levels again too. And those energy levels are represented by the periods in the periodic table. And you guys are actually only responsible for knowing the first 3 periods and then about potassium and calcium in the 4th period. Otherwise, you'll learn more about the other levels once you get on into chemistry. But we know that the first energy level represents the first period. And there are 2 elements in the first period. Those are hydrogen and helium. And since there are only 2 elements in the first period, there can only be a total of 2 valence electrons in that first energy level. The second energy level refers to the second period on the periodic table. There are 8 elements in that second period, which means there can only be a total of 8 valence electrons in the second period. And then the third energy level represents the third period, and it can only have a total of 8 valence electrons in it as well. And you may be wondering, how do I know how many valence electrons an atom will have? All you have to do is take a look at the periodic table and remember the pattern that I showed you guys. On your periodic table, you can kind of see it here, you have your group 1, which is over here, and then you have group 2, and then you have groups 13 through 18, which are right over here. Group 1 elements have 1 valence electron. Group 2 elements have 2 valence electrons. Group 13 have 3. Group 14 have 4. Group 15 have 5. Group 16 have 6. Group 17 have 7. And Group 18 have 8 valence electrons. And you can follow those patterns to determine how reactive an atom is and how it's going to combine with other atoms to form compounds. So now we're going to talk about chemical bonds. And we know that stability is reached when chemical bonds are formed. Bonds are nothing more than forces that hold atoms together in a compound. And in our last chapter, we talked about ionic compounds, and we also talked about covalent compounds, but we're really going to learn more about those in this chapter. But an example of how a chemical bond is formed, here we have an atom of sodium, and we also have an atom of chlorine. And we know that when sodium and chlorine combine, it makes sodium chloride, which is nothing more than table salt. But you can see in the illustration that sodium has a total of 11 electrons. One of those electrons is valence in the third energy level. And coincidentally, sodium is a group 1 element. And we already know that group 1 elements have 1 valence electron. Chlorine has 7 valence electrons in its outer shell. It is a group 17 element, and so it has 7 valence electrons. And what happens in this kind of compound, sodium donates its 1 electron, and chlorine needs that 1 electron, and so it takes it. And you can see at the very bottom I have the electron dot structures of those elements. And when that happens, when sodium gets rid of its 1 electron and chlorine gains it, sodium becomes very positive and chlorine becomes very negative. And because opposites attract, you have an ionic compound. The sodium and chlorine are very, very attracted to each other, and so they hold on together in a compound. But we know that ionic compounds are not the only compounds that can form. We also have covalent compounds where electron pairs are shared. And so another excellent example is water. The formula for water is H2O, and that formula tells us that we have 2 atoms of hydrogen and 1 atom of oxygen. And those electrons can be shared between atoms so that their outer shells are filled. Oxygen is in group 16, and it has 6 valence electrons in its outer shell. Hydrogen is a group 1 element, and even though it's not an alkali metal, it still only has 1 valence electron in its outer shell. And you can see in this particular illustration that each hydrogen, it looks like its outer shell is full with 2 because the first energy level can only have 2 valence electrons. And if you count, you'll see that oxygen also appears to have 8 valence electrons. That's because hydrogen and oxygen are sharing pairs of electrons, so it makes their outer shells feel like they're full.